So, for the following 10 to 15 minutes, I want to just formally define two terms for you. One is called the training error. The other one is called the testing error. Again, the training error will be applicable to all models. The testing error will be applicable to all models. So I want to define the first term called the in-sample error or the training error. So this is the same as training error. Okay, so what do I define? Well, the training error, of course, you need to look at the training samples. Here you have all the xn's, and then H is your hypothesis. So H is one of the hypotheses that you choose. That's not the final hypothesis. Okay, so this is just one hypothesis in the hypothesis set that you are going to evaluate. I want to see how good is the current hypothesis that I'm considering. Okay. So this is your H, and then F is your unknown target function. So if your hypothesis applied to your training sample is equal to the target value, then you will be happy, okay? And then that will give you that should give you a very small error. If they are different, that should somehow accumulate over all the samples in your training set, and they will add up, and then they will give you the overall in-sample error or the training error. So, what I would define the in-sample error is the following. You look at this equation. On the right-hand side of this equation 1, you have a summation over all the training samples, n going from 1 to n. Capital N is the number of training samples. You have 1 over n, that means you're taking the average. Inside the summation, you have this indicator function. This bracket means that the thing that's inside will either give you yes or no. Okay, so if the statement inside is true, you will report a 1. Otherwise, you will report a 0. Okay, so that's the indicator. Now, what am I looking at? I'm looking at whether my H will be the same as my F for that particular xn that I am looking at. So if H is the same as F, you have 0 error. That means you have correctly classified that sample. If it is wrong, you give a 1. And you add things up. That's really like the perceptron algorithm, the hard perceptron algorithm. You either give yes or no. Okay? So that is the training error. Now that is pretty much how you would train your deep neural network. Of course, you may not exactly use this formulation. You may use the cross entropy loss, but that's like a proxy to this training loss. I'm going to focus on this training loss because it'll be easier to analyze. Okay, so that's the training loss. And then I am going to define a thing called the testing error, okay, or the outsample error. So this is this same as testing error. So this testing error also has a sample X, but now this X is not coming from a training set. It actually is a sample drawn from this distribution P. Okay, now look at this thing here. The training error, this is xn, is one of your training samples. You are just evaluating your error for all the training samples. The testing error is not evaluating in your testing set. Okay, that small testing set that you use when writing a paper. That X comes from the entire distribution, that comes from your population. Okay, so that is your X. H is your hypothesis, is still the same current hypothesis that you're considering. And then F is the unknown target function. If they're equal, then you say that it is correctly classified. And since X is drawn from this P of X, you cannot just write the summation of all the samples because you have infinitely many of these X. So what should you do? You should measure the probability. Okay, you should measure the probability, and this probability is, what is the probability that HX is not the same as your FX? This is actually very similar to what I'm defining here. Here you have the indicator function of h not equal to f. Here you also have h not equal to f, but you are evaluating on all the samples coming from your entire P. And I'm looking at the probability. Okay, that will define my out-of-sample error. So in terms of notation, I call it E out, error out. Here I call it error in sample and out sample errors. Okay. Now, what do you want? Of course, you want the in sample error to be as close to your out sample error as possible. Why? If you can make that happen, then by minimizing your in sample error, you will be able to minimize your out sample error. And you'll be very happy because you're looking at the training stage, you minimize the training error. If the training error can be suppressed as low as possible, and if they're equal, then you can guarantee to make the testing error to be small as well. Of course, we know that life is not that easy, so we need to do a lot more analysis to make this happen. But before I do that, I want to draw a connection between these two errors to make it extremely clear of what they are all about. The in-sample error or the training error, as I have described, it is the average of this indicator function. Now, when you look at this expression, it is a finite average. Okay, it's a finite sum over 1 over n. That is the finite average. Now, in statistics, we call it the sample average. The outsample error is defined as the probability that your target function doesn't match with the hypothesis function. However, this probability, I can also expand it using the following equation. Now, what is the equation here? I can multiply the 1 with this p, and I can multiply 0 with this another guy. Okay, what are they? Well, that is just the event that h is not equal to f, and here is the event that h equals to f. Alright, so if that happens, you can see that this is 0, this is 1, I will give you the probability. And now if you look at the sum of these two quantities here, this is like a Bernoulli event. Right, so you have, let's say if you have a random variable z, that is Bernoulli. Okay, so you have either going to 1 or 0 with probability p and probability 1 minus p. I ask, what is the expectation of z? That is just 1 times the p plus 0 times 1 minus p. That will give you p. Right, so the expectation of a Bernoulli random variable is exactly the same as the probability of getting ahead. And so here, you can see that this is the probability of getting this event. That is the same as the expectation of this event. Where all the x is drawn, now you don't have this xn. Okay, so it's the expectation of all the x where x is drawn from p. So when you compare these two, this is the finite sample average. This is the expectation. As n goes to infinity, these two, in principle, should become the same. Okay? But when n is small, then it's unclear how are they related. So we need to do some calculations. So the role of this probability, p, is very important. It is going to generate the training samples, which will define this training error. Is also going to generate the testing samples, which will give you the testing error. The biggest question we don't know yet is how close is this in-sample error compared to the out-sample error. And that is the place of discussion. Okay, so we will spend a lot of time on these. Now, to give you a preview of what we are going to do, I want to just mention a thing called the half-day inequality. We will spend another lecture on just going through the details of these inequalities. This is a very powerful inequality that can help you address the problem that we are asking here. The reason is, you look at the equation in the in-sample case, it is really the summation of yes and no, right? 1 or 0. whether it is true or false. Okay, so because you're looking at this yes-no situation, there exists a set of mathematical tools in the probability inequality literature that can help you analyze the probabilities. So imagine that you have a sequence of IID random variables, and then all these xn is between 0 and 1 with the mean being a mu. You can always ask the question, how far is your sample average compared to the true average when this deviation is bigger than certain epsilon, and you can hopefully find an upper bound. Now, if you can find this upper bound, you will be able to say that the probability that this will be bigger than certain epsilon has to be somewhat big or small, and how is it going to change as my number of samples going to become bigger or not. So you go back to this situation. Since you're looking at true and false in this summation, you're literally running into this problem, true and false. And what is the mu? Well, the mu, as I have said, this is the expectation of that. And so that should be the mu. The mu should be your outsample error. And that will be your in-sample error. You want to quantify the gap between your in-sample error and the outsample error. So we need to have some mathematical description of that, and the conclusion is it will be upper bound by this quantity. Now we're going to derive that next time, okay? But if you look at this expression, it tells you a lot of interesting things. As n going to infinity, okay? As n going to infinity, this quantity is going to 0, okay? Very, very rapidly, and therefore you will be able to ensure that your in-sample error is going to be very close to the outsample error as n grows. Makes sense, because the more training samples you have, the better you will get. Okay? Alright, so we are going to look at this problem more carefully next time, and I will introduce this probability inequality. And so I will encourage you to take a look at the lecture slides and get an idea of what are these inequalities. These are usually taught in the probability course. If you're taking it, you should be okay. But if you haven't taken it, take a look. It's not that difficult. Okay, we just sit down and then we'll go through it together next time. All right. Okay, so this is the end of today's lecture.